Howdy, today I'll be solving the third exam from 2015 to hopefully help prepare for the exam. So let's get started. So we have a very thin wire that lies in the XY plane, and the shape is shown as below, which is a quarter circle. Two circular segments is what it says. Centered at the origin, connected by segments along radii. There is a current I flowing in the wire as shown, and it wants us to find the magnetic field at the origin. So anytime we want to find the magnetic field for like weird objects like this that are not straight lines or solenoids, which are coils, we're going to use Biot-Savart's law, which is dB is equal to mu naught I over 4 pi ds cross r, where ds is the length in r cubed. R is the r vector from ds to the point of interest. So if we look at our shape, we have 4 segments. So I'm going to call the segment big A, like the straight line. The bigger quarters, like the arc, the bigger arc, I'll call that B. I'll call the smaller, not smaller, but like the other long straight segment C. And then the smaller arc, segment D. So if we look at segment A and segment C, we should realize that the field is 0, right? So B is 0 at A and C. You may be wondering why. Well, if we create our ds vector, right, on A, ds will point this way. And r points from where ds, like where we start our ds, to the point of interest, which goes this way. And if we notice, these are parallel vectors, right? So the cross product of this is going to be 0. Same for, same for C. If I draw my ds vector, which by the way goes in the way of the current, so ds will go this way. That's hard to see. ds goes this way, and r also goes this way, which they're still parallel, so the cross product is equal to 0. Even though they're going different directions in segment A, they're still parallel to each other, so the cross product is going to be 0. So it's A, B, C, D. So segments A and C are equal to 0. So basically we're just dealing with the arcs in this case. So I'm going to start with B. So at segment B, I have my ds going along the arc, right? So ds is going this way. And my r is going this way, pointing to the point of interest. So when I write Biot-Savart's law, it's going to be dB is equal to mu naught I over 4 pi ds cross r. We see that this creates a 90-degree angle, right? So it's just going to be ds. And then r, where the r vector is going to be the radius b of the big arc, so b, divided by b cubed. Then now I need to determine what direction it's going in. So if I put my palm on ds, right, and then I curl my fingers towards r, I get that my thumb is pointing into the page. So this is going to be into the page. Right? And then all I need to do is I need to find b. And to find b, I got to integrate both sides. So I take the integral on both sides. So b is equal to, I can pull out the constants. So mu naught I divided by 4 pi. B divided by b cubed is b squared. And I'm left with the integral of ds, right? Where ds is the length. In this case, it's a quarter circle with a radius of b. So it's just going to be pi b. It's going to be pi little b. Right, because circumference is 2 pi b. Oh, it's actually pi over 2. It's my bad. It's pi over 2 because it's a quarter circle, right? So it's a fourth of this. So it's pi b over 2. And then I multiplied by mu naught I over 4 pi b squared. This simplifies to mu naught I over 8b, and it's into the page. So that's the first part. And the second part follows the same process. So if I go along the little arc, let me Let me erase this now. So if I go along the little arc now, let's say I want my ds to go, I don't know, let's make it go this way. My r vector points from where I started my ds to the point of interest, so it points like this. Notice how it's still 90 degrees, so there's no angle to worry about. So at segments, what did I call it? Segment D, I get dB is equal to mu naught I over 4 pi, and then I have ds, right, which is just ds, and then r, the r for this little arc is little a, so a divided by a cubed. And then if I do the cross product now, if I put my palm on ds, right, and I curl my fingers towards r, I get that now my thumb is pointing out of the page, right? So this one is going to be out of the page. And then similarly, like the last one, we just integrate to find b. So b is just mu naught I, gather my constants, 4 pi, a divided by a cubed is a squared. ds is the same, right? They're both quarter circles. So it's going to be, instead of pi b over 2, it's going to be pi a over 2. This simplifies to mu naught I over 8a, and this time it's into the page. So the total magnetic field, so I just put B total or something, is equal to mu naught I over 8a out of the page plus mu naught I over 8b into the page. And that's how you solve number 1. Not too bad. Now for number 2, we have an infinitely long cylindrical hollow wire. So that's probably a good indication we're going to use Ampere's law. The wire has an outer radius b, and it has a hole with the center radius a. It wants us to find a magnetic field everywhere. So yeah, we're going to use Ampere's law. If a known current I flows from left to right. So let me just draw it. So current's flowing from left to right. And the current is uniformly spread. It's really important to know that current is uniformly spread over the region between A and B. And then there's a second force question, but we'll address the first question right now. So the first question, we're going to use Ampere's law, right? The first part. So it's going to be the integral on a closed loop, b dot dr, is equal to mu naught I, where I is the current enclosed. So for r less than a, we're in this region, right? And the problem said that it has a hole. Even on the side view, we see it has a hole. So we're in here right now. And, well, there's no current. There's nothing in there. So the magnetic field in that region is 0. Or it should be little a, not big A. So now for my second region, when I'm between A and B, I'm in here now, which in the side view would be right here, which we do have current uniformly spread. So it's going to be B, and then 2 pi r, right, from our loop, is equal to mu naught I divided by the actual area of this wire. The actual area is pi b squared minus the whole, so pi a squared, and then times where our loop is. So our loop has an arbitrary radius r, so it's pi r squared minus pi a squared. And then I could factor out the pi's if I wanted to, so the pi's would cancel here. But basically my answer would just be that b is equal to mu naught I over 2 pi r squared minus a squared over b squared minus a squared. And then for my last region, when I'm outside of the wire, so I'm out here on the side view. So r greater than b, I get that b 2 pi r is equal to mu naught I divided by the actual area of the wire, just pi b squared minus pi a squared, times the area of where my loop is. So we see that our loop is like bigger than the actual wire, right? So our loop is going to have the maximum amount of area, the max area that the wire has. So it's going to have the same area, pi b squared minus pi squared, right? Because anything afterwards is empty space, right? Our wire stops here. Like there's nothing going past it. So there's no extra area that we could possibly add. So when we do this, we notice that they cancel. So B, which is equal to mu naught I over 2 pi r. And then if it did ask you for the direction, I don't think this one did in particular, like on the answer key. But if it did, you put your thumb in the direction of the current, right? So like it's pointing to the right. The ways your fingers curl is the direction of the current. So then all the magnetic fields will be clockwise in this case. So that's how you determine the direction. Now for the second part, we want to find the force that the wire would exert on a thin, straight length of wire W located at a distance 2b. So let's say right here, 2b, like a wire or something, 2b, for length of W. From the axis of the cylinder, that thin wire had a current 3I flowing through it. So this has 3I flowing from left to right. So like that. The side view would be like this, pretty much, 2b. Actually, no, it would be like up. So, like here, I guess, 2b. So, for a wire, recall that the force is dF is equal to I ds cross B, right? But in this case, if we want to find B at a particular point of 2b, right? Our radius, okay, so 2b is going to be when we're outside of the wire, right? So we're going to be using this equation, right? Boxed in red. If we want to find a particular point 2b, our radius is going to be 2b, right? We're going to have like a loop like this, pretty much. And because we're going to have 2b at that point, the magnetic field is going to be constant. So then I can rewrite this as F is equal to I, and then I'll just do the cross product right now. So B, let me write B right now, which is mu naught I, where the current enclosed is now the 3I. So 3I divided by 2 pi, and we're at 2b, right? So 2b. And then ds is the length. The length is w, so this is w. So this simplifies to 3I squared mu naught w over 4 pi b. And now to determine the direction, well, our current is pointing to the right. So from our magnetic field, if we curl our fingers, when we get up here on the red, like the red surface I drew, out here my fingers are pointing out, so the field's pointing out. But down here, my fingers are going in, right? And then I put my palm, because the formula is ds cross b, right? So I put my palm on ds, which is the length of the wire I'm interested in, which is the length of w. And then I curl my fingers into the page, right? Because that's where the magnetic field is pointing in this case. So then my thumb's pointing up. So the direction of this force is up. Or I think the answer key had it as an up arrow. So yep, that's the answer for that. Now 3 and 4 are little interesting. They're interesting problems. So a rocket, but this one's not too bad. The other one's kind of, number 4 is a little BS thing. Let's see right now. A rod can slide on 2 frictionless, resistance-free rails. The rods are connected by a battery of capacitor as shown. So because we have a battery, we don't have to use lenses long. We're going to always make current come out of the battery. So let me do that right now, actually. So current's going this way. And because my current's going this way, I would always want to make plus Q the way my current's going, and minus Q the other side, the capacitor. The rails, there is a constant vertical magnetic field with magnitude B naught. The rails are at an angle theta with the horizontal plane. the rod is somehow moved up by the rails by some external force, so that its velocity along the rails is a constant magnitude v naught. So the rod's getting moved up like this, velocity v naught, and the charge of the capacitor is 0 at t equal to 0. So that's going to be our initial condition. If the rod has a resistance R, so this has resistance R, and we're ignoring self-inductance, find the charges on the plates of the capacitor as a function of time. So whenever you have something like that, finding a function of time, we're going to use Faraday's law, which is the integral of E dot dr is equal to negative d dt, or the partial derivative, however you want to write it, p dot ds. I think it has it as the partial derivative here. No, it has it in d dt. I mean, either one's fine. You need to know that you're gonna take the derivative with respect to time. So we always go along ds this way, right? Because by convention, that's how the book does it. You don't have to go along this way, but I would recommend going like this. So we want to find the flux, right? Just the integral b dot ds. And then b is pretty easy because b is constant b naught, so I can take that out of the integral. But what is ds? In this case, we have to actually look at like a side view pretty much of this as an incline. So we see this incline, right? This is 90, this is theta. So my b is pointing up, right? Okay, so yeah, my b is pointing up. So suppose like I'm looking at the rod from like this side, right? So I'm seeing the currents like right now at this point. So my b is always pointing up from the plate. So this is pointing up. Oh. This is pointing up. This is b. But ds, in this case, ds is not length. ds is the area vector. And you remember with Gauss's law, ds is always perpendicular to the surface. So ds is pointing like this. So it's not perfectly perpendicular. We need to find basically what angle that is. And we can do that by, let me elongate my vectors. So let me stretch this down. Let me stretch this out like this. So basically the way we determine like where theta is in this triangle is I see what sides are perpendicular with the green and blue wire. So if I look at vectors, so if I look at the green vector that I drew, I see that this line I'm drawing in red, this is perpendicular, right? 90 degrees. And then I want to find the segment that's perpendicular to the blue wire, and I see that it would be this segment, right? This 90 degrees. So basically, it's saying that the red and green segment, yellow segment, is going to have the same angle as the blue and green segment. So that means this is also going to be theta. Right? And then my area, I'm pulling my rod to the right, right? Like the rod's getting pulled to the right. So that's going to be increasing this length right here. And I'm gonna just call this a length x, right? And then I want the x component, so I'm going to need the cosine. This is ds, by the way, the green vector. I'm going to need the cosine component of ds pretty much. So then my area, which is going to be b naught, it's going to be w, right? Because w stays constant. But then x is changing. So I'm going to have wx. And then the plane's at an incline, so it's going to be cosine theta. And now I need to take the derivative for flux. So d dt is equal to b naught w cosine theta. Do not differentiate theta. We're differentiating like x or y or whatever. So this is dx dt. And then because I'm pulling the rod to the right, as I pull it to the right, x gets bigger and bigger, right? So this is gonna be positive v. V naught? Yeah, v naught. Yeah. So this is equal to b naught w v naught cosine theta. And then that's it. I just gotta basically create my equation and then solve the differential equation. So I'm gonna go around my loop like the way I define, right? Because that's how the book defines it. So if I go around my loop now, I get plus v, and then my current touches the positive part of the capacitor, but because I'm going the opposite way, it's going to be negative q over c. And then when I get to the rod, at this point, my ds is climbing up, but my current is going down, so it's going to be negative IR. And this is equal to negative, right? Negative from the law. Cannot forget this negative. Negative b naught w v naught cosine theta. And then I'm going to move the v to the other side. So if I move v to the other side, I will see that I will get negative v, right? So I'm going to just divide by negative on everything. So I would get IR plus q over c equals b naught w v naught cosine theta plus v. And then we want to solve the differential equation in terms of capacitance. So recall that I is dq dt. And this case it's positive because current is touching the positive part capacitor. If it was touching the negative part, it'd be negative dq dt. But because that's why I like defining plus q in the same way the current. So you don't really have to like think about if it's positive or negative. If you do it this way, you're always gonna have it as positive. And then the negative sign just depends on how you go around your loop. So I can rewrite this as dq dt, dq dt of r plus q over c equals b naught w v naught cosine theta plus v. And we should recognize this is a non-homogeneous differential equation, which just means it doesn't equal to 0. And whenever we have this case, we need to know that the solution is q particular plus q homogeneous. So let's solve for q particular. In q particular, this is in steady state. So basically any rate of change with time is equal to 0. So I will have q over c, or I'll put qp in this case, I'm solving for qp, is equal to b naught w v naught cosine theta plus v, or qp is equal to c, b naught w v naught cosine theta plus v. Pretty easy to solve for that one. Now for qh, we need to assume that q homogeneous has a solution of alpha e to the negative beta t. And basically what we're going to do is we're going to plug this in for any q's. So I'm going to plug this in here. I'm going to take a derivative in that case, and I'll plug it in for q here. And then I'm going to set this equal to 0 instead of the b naught stuff, because this is the homogeneous solution, which means it's equal to 0. So I'm going to get the derivative if it's itself, right? So alpha e to the negative beta t times chain rho, which is negative beta, times r, right? Plus alpha e to the negative beta t over c is equal to 0. And in this step, you always solve for beta. So divide by e, divide by alpha. You always solve for beta. I'm going to move the c to the side. So I'm going to get negative beta r equals negative 1 over c, or beta is 1 over rc. By the way, if you get a negative for beta, you did something wrong. Like, you can never have a negative for beta here. So if you got a negative, check your signs, check the way you define your loop, because there could be a mistake somewhere. It should be positive. So now that I found beta, I'm going to plug everything back in to this equation in yellow. And then I'm going to solve for alpha by using my initial condition. So q at t is q particular, which we found is c, beta naught w v naught cosine theta plus v, plus q homogeneous, which is alpha e to the negative t, beta t, which is t over rc. And my initial condition told me that the capacitor has 0 charge at t equals 0. So basically at q equals 0, my function of capacitance should equal to 0. This equals to c b naught w v naught cosine theta plus v plus alpha e, and I plug in 0 for t, right? So e to the 0, so that's just 1. I solve for alpha, I get alpha is negative c beta naught w v naught cosine theta plus v. And then I put it back together into q of t. So q of t is equal to, I'm going to factor it out, right? So c b naught w v naught cosine theta plus v. And this is 1 minus e to the negative t over rc. So the main thing with this problem was understanding the rod. That was one thing. The second thing is, for non-homogeneous differential equations, which is this one, meaning not equal to 0, meaning, so if the flux is 0, it's a homogeneous equation pretty much. In this case, the flux isn't 0, so it's a non-homogeneous differential equation. We have to use this form, QP plus QH, and then we just solve for the rest of it and we get our answer. So now for this part, this is one where it has a little bit of BS, because you need to understand like a Cal 3 chain rule for this question, but let's start with it either way. An infinitely long wire carries a constant current as shown, so it carries a current of I naught. Nearby is a rectangular loop with resistivity rho and a cross-sectional area A. It has dimensions W and H as shown. The loop is originally a distance P from the wire. At t equals 0, the loop begins to move a constant velocity v naught in the y direction. Ignoring self-inductance, find the current that will flow in the loop. So for this one, it's also going to use Faraday's law. So it's the integral E dot dr is equal to negative d dt of B dot ds. And we're not given the magnetic field, so when that's the case, we're going to have to use Ampere's law. Like whenever we have like this long segment, we're going to have to determine our own magnetic field by using Ampere's law, which is the integral of B dot dr is equal to mu naught I. And close. So let me start with the wire, because that'll be pretty easy. So I'm going to create my loop like this, right? So that's going to be B 2 pi r is equal to mu naught I naught, because the current of the wire is I naught, right? So then B is mu naught I naught over 2 pi r. And we have to determine if it's into the page or out of the page. So if I put my thumb along the direction of the current and I curl my fingers, when I'm at the bottom, right, like to the left, my fingers are pointing out. And then when I curl them back, like across the wire, they're pointing in on this side. And I care about where the circuit, like this, where this box is. So it's going to be into the page. So magnetic field is into the page. And then ds, we always go along this way because the book does it this way. And now I need to determine my direction of current induced by changing it, right? There's a change of flux because I'm changing like how far away the wire is going. So as I go down, right, I'm pulling it further and further away from the wire. So the radius here is going to get smaller, right? So B, this is using Lenz's law, by the way. So B is decreasing. Because B is decreasing, the flux is also decreasing. That means B self is same as B. Or that B self is also into the page. I'm sorry, also out of the page. Which means current is counterclockwise. So my current is going like this. Right. So now we need to find the flux. Flux is the integral of B dot ds. And whenever we have B and if it has like t or time, that's fine. We can take it out of the integral. In this case, we have r. So like whenever we have r or x or y, like in this case, I'm gonna change it to y in a little bit. Like whenever it varies on distance, you need to keep it in the integral. So It's going to be the integral of mu naught I naught over 2 pi r. And then, what is ds? Well, as I go around, as I create more and more magnetic fields, right? So if I create like a magnetic field like this, that's not going to have the same area as if I had one right here, if I had one here, or so on. So I'm actually have to kind of take little slices of this where the width is going to stay the same, but this I'm going to call dy. That little segment's going to be changing. So because I'm calling that dy, I'm going to call this y as well. So that's how the answer key has it. That's like the only reason. So put that y. And then my area is going to be w, right? W staying the same. But then I'm climbing up the y, which is dy. Now, this is where things will get a little... Like, this is where things start to begin to get a little interesting. So, you would think that your initial bound would be like p, because we have initial height of p. But that's actually wrong, because if we did say it started at p, right? Let's say we said it started at p. And then we said it went to like, I don't know, like to y, for example. That you're saying that it's always going to stay at p, and then you're basically going all the way to some point y, which is wrong because you're going to make this box longer than it actually is. Does that make sense? If you set your bottom bound as p, you're saying that you're always starting here at this green dot. You're saying you're always starting here. And then if you say your top bound is like y or something, you're saying that you go to some point y, which would actually make this box longer, which is not what's happening. However, p does play a role into it, because we need to create a function of y in this case. So y is a function of time. We're just going to be using a bit of kinematics pretty much. So at time equal to 0, I have my height p, right? I'm a distance p away. And then basically I need to account for how much y is changing. And I know that x or y or whatever is the integral of velocity dt, right? And I know that has the velocity, or in this case y, right? Y is the integral of v dt. So I'm gonna have, I know my velocity is, wait, do I know my velocity? Yeah, I do. My velocity is v naught. So I'm gonna have v naught, and I integrate with respect to t, which is t. So this is the y I'm talking about. So basically my bottom bound is not gonna be p, but it's gonna be this y that I found. Likewise, I have to account, so that's accounting for this, right? So it's accounting for like when the box moves. So if I draw it on like a side pretty much, let's say it was like lower, this point will be p plus v naught t, which is good because that means we're not making our box bigger, we're keeping it the same. But then, and this was called y, right? But then our box has a height h, so then this bottom bound is to cover the entire box, which is y plus h. Does that make sense? So my top bound is going to be y plus h. Now I integrate, I get mu naught. Oh no. First, let me determine if it's positive or negative with b dot ds. So I define ds to always come out of the page, right? And then from the wire, I get that b is also out of the page. So in this case, it's positive. So I got kind of lucky there. But if b was into the page at this point, you would have a negative outside because the dot product is 0. But in this case, we're not going to worry about that. So you got to integrate. So it's mu naught I naught w over 2 pi, and then it's ln of y plus h over y. I'm going to simplify this a little bit. So it's ln of 1 plus h over y. Now here's where it's a little dumb. You kind of need to understand Cal 3 for this. So you have d dt and the flux, right? We're just going to take the time derivative, right? So we have mu naught I naught w over 2 pi. And the thing that's dumb with this question, pretty much, is that you're going to take the derivative of ln, right? So you take the derivative regularly, but then you're going to have, or let me take the derivative of ln and then let me write what I'm saying. Actually, let me write this again. Mu naught I naught w over 2 pi ln of 1 plus h over y. So if we take the derivative of the log function, right, it's 1 over itself, right? So 1 plus h over y. And then this is where the word thing comes in, because you're taking the derivative of the inside with respect to y, right? So d dy. But we need to take the chain rule to get dt, because this is what we call an intermediate value, pretty much, if you take in Cal 3. So then you have to multiply by the chain rule, which is dy dt. Which is really dumb. I'm not sure why they would put this on this exam. So what I'm saying is you're going to take the derivative of the inside with respect to y. Derivative of 1 is 0. Derivative of h over y is negative h over y squared. And then times the chain rule with respect to time, which is dy dt. So this part, we wanted to find dy dt. So you have seen it in Cal 3, it's d dy. And then this goes on the top, up here, which is dy dt. Again, I'm not sure why they would put this on the exam. So hopefully it's not on there, but that's why I wanted to solve this one too, because it's kind of weird. So let me just simplify things. d dt of the flux is equal to mu naught I naught w over 2 pi. I'm going to find a common denominator here by multiplying in here. By multiplying by y, right? So I'm going to get y over y plus h. And then I'm left with negative h over y squared. And dy dt is the same as like if it was dx dt, so it's just velocity. And since velocity is going down in the positive direction, it's just positive v. So v, or v naught, right? That's what it was. So now I'm almost done. I just gotta solve currents. So I know I'm going around my loop, right? I go in the same way direction, which is I. The wire has a resistance R, which I actually haven't solved for yet. I should do that. So what is R? Well, we're told that it has a resistivity and cross-sectional area, right? So we're going to use rho L over A. In this case, rho is giving us rho, cross-sectional area is little a, and the length of the wire is just a perimeter. So that's 2W plus 2H. So this is the R I'm talking about right here. And this is equal to negative from the law, right? And then mu naught I naught W over 2 pi. Notice how a Y up here cancels with a Y down here. So this is negative H over Y plus H. Right, because I still have a Y in here times this. V naught. The negatives cancel, and then I'm just going to divide by R, might as well. So I is equal to mu naught I naught W H V naught over 2 pi R Y plus H counterclockwise. That's how we determine a current, right? It's already going counterclockwise. So again, I'm not really sure why they would put something like that where you have like an intermediate variable. You need that type of chain rule. But now you know how you solve it, right? And the rod one is not too bad as well, as long as you recognize how to find theta. And you have to recognize you need the x component because you need respect to x when it's changing. So, yep. Hope this helps. Good luck on your exam.